Hello everyone. We will discuss Bezier splines in this lecture. So we have already seen cubic splines and we have seen how we can use cubic splines to interpolate between endpoints, right? Piecewise cubic splines. However, given 2 points, if we join them with cubic splines, we do not quite have a handle on the shape of the cubic spline, right? The cubic spline has this kind of inflection in the middle, which we can't really control. And the other point about modeling with cubic splines is that you have to specify the starting and the ending tangent, which is not always simple. So as an alternative modeling strategy, let us try and use what are known as Bezier splines. So Bezier curves were introduced by Pierre Bezier, who was an engineer for the French automobile company Renault. And the good thing about Bezier splines is that to specify a Bezier spline, you just need to give the positions of points that lie on its control polygon. So let us look at what does that mean. A Bezier spline PT is defined as Bi into JNIT. Here Bi's are the control points and here I varies from 0 to N, B0, B1, B2, B3 for a cubic Bezier spline. These B points are points on a control polygon. The Bezier curve will not pass through all these points. It will only pass through the first point and the last point of the control polygon. It is guaranteed to pass through the first and the last point, but it will usually not pass through any of the intermediate points. What is JNI, T? It is this basis. This is our way of writing N choose I. N choose I is this, in case you have forgotten, multiplied by T to the I, 1 minus T to the N minus I. This particular basis is called the Bernstein basis. The Bernstein basis gives Bezier splines certain very desirable properties, and we will see in a bit what those properties are. The first thing that you should notice here that the Bezier spline is already written in the form of geometry multiplied with some blending functions. Okay, so the blending functions are the Bernstein basis functions and the geometry are the points on the control polygon. Now let us look at some properties of the Bezier splines. For any value of t, the Bernstein basis functions, they will add up to 1. So you can verify this later by yourself. The Bernstein basis is also always positive. So n choose 0 and n choose n are defined as 1. N choose I is 0 if I is outside the 0 n span. And n choose I is greater than 0 whenever I is between 0 and n. Okay. So this property is called positivity, and the fact that the JNIs will add up to 1 is called a partition of unity property. So the basis functions, they form a partition of unity. If we take a particular degree of the Bezier spline, so we say that we are interested in cubic Bezier spline, immediately it should be obvious to you that it will have 4 control points. So the degree of the Bezier spline is equal to the number of control points minus 1. Corresponding to the 4 control points, you will have 4 basis functions. So J30, J31, J32, J33, and they will have this form. each one of them is a cubic polynomial, which is not surprising because the degree of the Bezier spline has to be 3. And if you plot them, you can immediately figure out certain properties of the Bezier spline. The parameter value for the Bezier spline always goes from 0 to 1. So the parameter range is always normalized. When t is 0, the only basis function that is alive is J30. Other 3 basis functions go to 0. So at t is equal to 0, since only J30 is 1, P of 0 is equal to B0, right? So the curve passes through the first control point. Similarly, if you substitute t is equal to 1, you will find that all the basis functions except J33 will go to 0. So P of 1 is equal to B3. So it will also pass through the last control point. So these points are easy to prove. You can also write the cubic Bezier spline as this monomial basis times this weight matrix times this geometry matrix. These two together form the blending function matrix that we had seen in the cubic spline lecture, and this forms the geometry matrix for the cubic Bezier spline. Now let us look at the shape of certain examples of cubic Bezier splines. So if you have a control polygon like this, right, where these are the shapes of the 4 control points, you can see that the shape of the curve is that. Similarly, you can see if the control points are located as follows, then the shape of the curve is like that. And you can see these other examples also. Can you wait on this slide for a moment, inspect these drawings, and think what properties of the Bezier curve can you figure out by looking at these examples? At least 2 properties should be fairly obvious. The first property that you can figure out by looking at these examples, and we will look at proofs of these. The first property is that the starting span is a tangent to the curve. The ending span is a tangent to the curve. This is true for all the examples. The other property that you can figure out is that the curve is always going to be contained inside the convex hull of the control point. It is never going outside the convex hull of the control point. So these 2 are very important properties. They give you a very strong handle on the shape of the Bezier curve. You are ensured, for example, that if you are given a curve like this, the curve is not going to start here and then do all sorts of things and then come back. There is another property that says that when a curve starts from here, it cannot sort of wiggle around inside the convex hull and come and satisfy the end tangent property. That property is not very obvious here. It is called the variation diminishing property, but we will see the statement of that property later. So here are some facts about the Bezier spline. The basis functions are always real. The degree of the polynomial defining the Bezier curve is 1 less than the number of the defining control polygon points. The curve generally follows the shape of the control polygon. The curve always passes through the first and last point of the control polygon. So we had deduced this by looking at the shapes of the blending functions, but you can prove this by substituting t is equal to 0 and t is equal to 1 in the equation of the curve and see that P0 comes out to be B0 and P1 comes out to be Bn. So I want you to go through this derivation and verify it for yourself. This property is known as endpoint interpolation. Then a very important property of the Bezier curve is that applying an affine transform to the curve, and by now you should all know what are affine transforms. Applying an affine transform to the curve is equivalent to applying the affine transform to the control polygon and then generating the curve from the transformed control polygon. So if I want to apply an affine transform M to this curve, which is given to me by P of t, then this transformed curve, so let us say the transformed curve is Q of t. So if Qt is equal to M times Pt, then Qt is also equal to the affine transformation of the control points. So if the control points here are B0, B1, B2, B3, then if I affine transform each one of these control points to get the control points for the transformed after the transformation as C0, C1, C2, C3, and I generate the curve from C0, C1, C2, C3, then that will also be the same curve Qt. Okay, how do you prove this? You say that a affine transformation Mx can be written as Ax plus L, where A is linear and L is the translation. Then if you apply M to P of t, you can just say it is A times the Bezier curve plus some L. Now this is L into 1. This 1 you can expand as this because of the property of partition of unity. Now you can take summation Jn comma I common and you have A times Bi plus L here, and this is the same as applying M to B of I, right? So applying the affine transformation to the curve is the same as applying the affine transformation to the control points and then generating the curve from it. This property is known as affine invariance. The relationship between the control polygon and the curve is invariant to the affine transform. The next property of the Bezier curve that we are interested in is called the convex hull property. And the statement is that the curve lies inside the convex hull of the control points. How will you prove this? To prove this, we first need a formal definition of the convex hull. So given a set of points x, such that x is made up of points x0 to xn, the convex hull of this set of points x is given by the set of points ch of x such that members of ch of x are convex combinations of the original set of points. And what is a convex combination of x0 to xn? It is this sum a0 x0 plus dot 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 an xn such that all the a's add up to 1, all the a's are non-negative, and all the a's are real. Okay? Given the definition of a convex hull, it is trivial to prove that this property is satisfied. Why? Well, just by simple construction, you can see that a Bezier curve is defined as Bi into Jni of t, summation I going from 0 to n, and if you consider that the Bi's are the x's in this definition and the j's are the a's in this definition, then you already know that the Bernstein basis forms the partition of unity. It has the property of positivity and the values are all real. So it forms a convex combination of the control points and therefore the curve lies inside the convex hull of the control point. Okay, so the shape of the Bezier curve is therefore constrained to lie inside the convex hull of the control point. If you want to visualize in your head what the convex hull of, say, points on a plane will look like, if you are given points on a plane and you want to think about what their convex hull will look like, you can think that you push board pins at all these points. So you are pushing board pins into the screen at all these points. Then you take a large rubber band around all these points and you leave that rubber band. Okay, what will happen? This rubber band will get stuck at the outermost point. Then the shape that this rubber band will get stuck at is the convex hull. So that is one way of intuitively thinking about the convex hull, but the formal definition is what helps us in proving this property. Moving on, Bezier splines also have the property of symmetry. That is, the curve formed by considering the control points from B0 to Bn and varying t is the same as the curve formed by the control points Bn to B0, T1 minus t. You get the same curve whether you consider the control points from B0 to Bn or from Bn to B0. You can also change the domain of the parameters. So suppose you have, instead of taking t from 0 to 1, you want another parameter that goes from a to b, simply by substituting t is equal to u minus a by b minus a. So if you substitute this, now you can plug in values of u from this range and you will still get the Bezier curve. So this is known as a parameter domain transformation. Then this is the property that I was talking about that controls the wiggliness of the curve inside the control polygon, and I'm going to state this without proof. The property is called the variation diminishing property, and it is stated as follows: the number of intersections of a given straight line with a planar Bezier curve is less than or equal to the number of intersections of that line with the control polygon. So what does that mean? Here is an example where we have vertices numbered from 0 to 22. So there are 23 points here. So the degree of this curve is 22. Now this is saying that if I take any arbitrary straight line, so this is a straight line. If I consider this straight line, then the number of times that this straight line can intersect the control polygon, so say it has intersected the control polygon 1, 2, 3, 4, 5, 6, 7 times, then it cannot intersect the Bezier curve more than 7 times. So let us see how many times it has intersected the Bezier curve. 1, 2, 3, 4. So 4 is less than or equal to 7. This is true, right? So you can take any straight line. So you can consider this straight line, for example, and the number of times that it intersects the control polygon is 1 and 2, and the number of times it intersects the curve is 1 and 2. So 2 is satisfied, right? So this just says that the curve cannot wiggle around more than the control polygon. This puts a upper bound on the amount of wiggliness that the curve can have. And this property is known only for planar Bezier curves. It is unknown whether Bezier curves in space or in 3 dimensions satisfy this property or not. Next, we make an observation about the tangent vectors of the curve. So given that the equation of the curve is given to us by Pt, then dp by dt will be the derivative of this, right? So here we have first computed the derivative of the basis function, which turns out to be that, and then we substitute it inside dp by dt to get a derivative of the curve. So if I now substitute the values at the beginning and at the end of the curve, then I will see that the first tangent is dependent on the first span of the control polygon. So b1 minus b0 is the first span of the control polygon, and the last tangent is the dependent on the last span of the control polygon. So we say that the tangent vectors at the ends of the curve have the same directions as the first and last spans of the control polygon. So I would again recommend to you that you do this derivation yourself and verify whatever is written on the slide is correct. Now once we have a handle on the tangent vectors, now we can join two Bezier curves with whatever continuity we want. So if I want to enforce C1 continuity between a curve PT and QS, then P prime 1 should be equal to Q prime of 0. So you can just substitute from these equations. So the P's have the control points as BI's, the Q's have the control points as CI's, and you get a condition that looks like C1 is equal to n by m, Bn minus 1 plus Bn, where n is the degree of the P curve and m is the degree of the Q curve. And remember, for C1 continuity, C0 continuity already exists, so therefore the first point of the second control polygon is the same as the last point of the first control polygon. So what does this mean geometrically? This fact, it means that the points Bn minus 1, Bn and C1 are collinear. They have to be collinear for these tangents to have the same direction and enforce C1 continuity.